Hello everyone, I'm DongHeun Han, a PhD candidate at the IXL lab. Today I will present history compression via language models in reinforcement learning HELM, a paper accepted at ICML 2022. The core idea in this paper is simple. Instead of training a memory module from scratch, we reuse a pre-trained language model as a history compressor without fine-tuning it. In RL, partial observability is a core challenge. A single observation often can't reveal the full state, so we need memory, typically using LSTMs or transformers. But training them end-to-end in on-policy settings is unstable. The data distribution shifts as the policy updates, causing overfitting. And transformers also need many interaction steps to train reliably. Now, here's the core intuition. Language evolved to compress and communicate past events. Humans summarize complex sequences into high-level abstractions using words and concepts. Pre-trained language transformer models have learned to do this well. They encode long histories into compact representations for next token prediction. So rather than learning memory from scratch, we can leverage a frozen LM model that already knows how to compress history. That's the motivation behind the HELM. Since language models are trained on text tokens, the core problem here is how to convert arbitrary observations from our tasks into a form that aligns with their embedding space. HELM has two main parts. First, the frozen hope field, a trainee-free adapter mapping arbitrary observations into the token embedding space. And the second one, a frozen transformer XL, a history compressor producing a compact memory vector. At each step, we combine this memory with a CNN encoding of the current frame and feed it to a lightweight actor-critic head. Only the CNN and shallow head here are trained, everything else stays frozen. So there is no need to fine-tune the language model or learn a task-specific token representation. Let's take a closer look at what frozen hope field does and what is critical in HELM. We want to feed images or game states into a language model, but LMs expect token embeddings, not pixels. To address this, we apply a projection to the observation to match the pre-trained language model's embedding dimension. So we need a way to convert arbitrary observations into something that looks like a language token embedding. That's what frozen hope fields does. It's like a bridge from any input modality to the LM's input space. One of the key goals of HELM is to keep everything within the input distribution of the pre-trained language model. So we want to avoid giving it inputs it's never seen before, because that can lead to unstable or unpredictable behavior. To do that, we don't use a neural network encoder to map observations into token space. If we trained a neural network encoder, it might produce vectors that drift off manifold, far from anything the language model was exposed to during pre-training. Instead, HELM uses a random projection. This approach requires no training and still preserves the important structural properties of the input. Supported by the Johnson-Leiden-Strauss lemma, we know that even a random projection can preserve relative distances between vectors with high probability. In simple terms, this projection gives us a way to translate our arbitrary observation into a rough draft of a token embedding of language models without training anything. Next, we treat the projected observation as a query and feed it into a modern Hopfield network. Inside this network, we store all the token embeddings from the pre-trained language model. You can think of them as a reference table, like a dictionary of all the tokens the model understands. The Hopfield network compares our query to all of these stored embeddings. It then applies a softmax over the similarities, in assigning more weight to tokens that are more similar. The result is a weighted average of real tokens, a kind of synthetic token that blends multiple embeddings based on similarities. Even if our input doesn't match any single token exactly, this mechanism gives us a representation that still lives inside the language model's embedding space. That's important because we are about to send it into a frozen transformer and we want to make sure it stays in distribution. This step may seem technical, but it's crucial for making HELM stable and robust. The output of frozen Hopfield always lies inside the convexol of real token embeddings. That means it's always a weighted mixture of actual tokens, never something strange or out of distribution. In contrast, if we used a trained neural network to generate input vectors, it might produce representations that are far outside the token space in regions the language model were never exposed to during pre-training. This is called off-manifold problem, and it often causes unpredictable or unstable behavior. But with frozen Hopfield, we are guaranteed that every input to the transformer is something that resembles valid language, even if came from a completely different domain like vision or robotics. This design choice is what allows HEML to safely use a frozen LMs with no fine-tuning. Once we have a fuzzy token from frozen Hopfield before, we feed it into a frozen transformer XL just like a regular language token. This mirrors how language models are normally trained. They process sequences step by step, updating internal memory at each time step. In HEML, we treat each observation in the RL episode like a new word in a sentence. Transformer XL doesn't just look at the current input, it also attends to its memory of previous steps. This lets it summarize past observations efficiently without reprocessing the full sequence every time. Over time, the final hidden state becomes a compact summary of the entire episode so far. Even though we are using the Transformer XL in a new domain like games or robotics, it's still doing what it was trained to do in language task, summarize a past sequence and to predict what comes next. Next, we combine this memory HT with the current observation OT, which we pass through a very small CNN to get a feature vector. Then we concatenate the memory and the CNN output. This combined vector contains both long-term memory from the Transformer XL and current visual input from the CNN. Finally, we send this combined vector into a very shallow MLP policy, which produces the policy output and the value estimate. Here we trained only this shallow MLP and the CNN with PPO. Everything else, the transformer and the Hopfield adapter stays frozen. Now let's briefly go over the experimental setup. ICML is compared against two baselines. First, Impala PPO with LSTM, which has a recurrent memory module trained end-to-end. And second, CNN PPO, a simpler feed-forward policy that treats the environment as fully observable, serving as a Markovian baseline. All methods are trained using PPO, the proximal policy optimization algorithm, to ensure fairness. Hyperparameters like learning rate, entropy bonus, and memory size are tuned through grid search. They evaluate HEML on two types of environment, mini-grid and ProcGen, focusing on tasks that require memory. First, in mini-grid, they use several small grid-style tasks that designed to test short to medium-term memory, like remembering the location of a key or door. Across these tasks, HELM consistently outperforms both baselines. Notably, it beats LSTM agent trained from scratch by a large margin, especially when the number of environment steps is limited. It also shows less variance across random seeds, highlighting its training stability. Next, in ProcGen, a more visually diverse and procedurally generated benchmark, HELM shows significant improvement in sample efficiency and learning stability. In minor and jumper tasks, where you need to remember platform layouts, HELM reaches peak performance much easier than LSTM PPO. In haste, which requires multi-step planning and object interaction, HELM's memory abstraction gives it a clear edge. To summarize the core contributions of this work, HELM offers a powerful and elegant idea. We can use language models as general purpose memory compressors for RL. They're already good at summarizing sequences, so instead of fine-tuning them or learning new memory from scratch, we can just reuse what language models already know. Of course, there are some limitations to consider. The transformer XL used here has about 257 million parameters, so inference cost and memory uses are non-trivial. Also, in environments where memory isn't that important, simpler feed-forward CNN-based policies can perform just as well or even better. But overall, it's simple, effective, and promises step toward modular reusable components in RL, especially in data-limited and partially observable settings. This is the end of my presentation. Thank you for listening. If you have any questions, feel free to leave it on the comment section below. Thank you.